Well, hi, everyone. Thank you very much for allowing me to present this, and especially how the whole talks were scheduled, because before I present this, there were really amazing talks that will allow me to go over some of this stuff easily. Okay, I apologize also in advance for any cat drama that might occur. Raised cat during pandemics, you probably all lots of you might know what it is. Anyway, so I'm here to present to you the LBTI hosts survey for habitable zone dust around nearby star. So host stands for Hunt for Observable Signatures of Terrestrial Systems. And my collaborators are Steve Ertl, Denis Defrère, Phil Hintz, Grant Kennedy, Bertrand Menesson, and the whole host team. And in particular, I would like to thank Steve because he's the one who actually gave me those slides. I'm typically a dynamicist, and I just joined the team and starting to do observations with LBTI. It's very exciting. But if you have any very technical question on what I'm about to present, I will shamelessly redirect you towards Steve. So just so you know. So here we're going to talk about Exoskele Dust. So a little bit of a definition. Steve talked about that very briefly, but I would like to expand a little bit on the definition of that. So usually we use Exozodi for short, and it's an analog to our solar system zodiacal cloud. So which means that it's warm or hot dust that orbits relatively close to the star. And I want to touch briefly onto the distinction between warm and hot dust. The rule of thumb is that the closest the dust is to the star, the hotter it is, and the shorter the wavelength it can be observed at. So in general, hot dust is seen in the near infrared and warm dust in the mid-infrared, which is what we see with LBTI. Something important to understand about exosodies is that in contrast with other dust population that you can find around other main sequence stars, these ones are not produced in situ through a collisional cascade amongst larger bodies like Kuiper belt or asteroid belt analogs. So we have to, it's simply a matter of dynamical timescales. And so these exosodies have to be replenished, but not in situ. So you have either comet evaporation, so bodies coming from further out in the system, or Poynting Robertson drag from debris disk. So basically you have collisional cascade among large bodies in asteroid or Kuiper belt analogs, and then this dust spiral onward onto the star through Poynting Robertson drag. So why are we interested in this? Well, we care about that. So I briefly mentioned that it was related somehow to population of larger bodies further out in the system. So it kind of gives us insights on the fact that there are cold population further out on larger scales, but it also gives us insights into the dynamics of the innermost regions around the star and actually near the habitable zone. And so here is the image of, this is a simulation, okay? So you have a 20 Earth mass planet at 1 AU around the sun-like star, and this is how we expect it to see it at 10 parsecs. And you can see you have asymptotal structures. So observing exosodies, resolving them, and seeing structure in them could give us valuable insights on the content in planets and their dynamics in the habitable zone. Well, now on the other hand, when I said mid-infrared, some of you might have connected the dots. So Beth told us earlier today that mid-infrared was probably the best avenue to observe directly, to do direct imaging of exoplanets in the habitable zone, where we might find life. But since at these wavelengths zodiacal dust is also emitting, it might create confusion for future ExoEarth imaging missions. So you can see here, these are the results of simulations. And so one Zodia is the the typical amount that we get in the solar system. And so we measure the brightness of zodiacal clouds in zodies. So you can see that you have a planet here at 1 zodi, 5 zodies, 10 zodies, you can still see it, but 10 zodies is somehow a threshold, and above it, you don't see the planet anymore. You see structures, which is super interesting, okay, but you cannot really image your planet directly anymore. It doesn't bode well for that. In any case, it's interesting. If you don't have the dust, you can see the planet, and if you have too much dust, you can see structures and still infer things about the planet. So how do we detect this exozodiacal dust? I gave you a clue. I told you about mid-infrared, but I wanted to stress here that we cannot really do photometry or spectroscopy, and this is actually illustrated here with this graph, which is the spectral energy distribution of Eta Corvi, which is probably one of the brightest exozodies that we know of. It's 2,500 times the levels of zodiacal dust of the solar system, and you can see that the levels are just above the stellar SED, the stellar emission. So, and what we want to look at, we want to know what are the typical level of exozodiacal dust around main sequence stars. And the threshold we're interested in is that 10 zodies according to our simulation. So obviously, if we want to go and detect much smaller dust levels, it's not going to be possible with simple photometry. So we need to spatially disentangle, and we need to resolve this dust emission from the starlight, which is what we use interferometry. So there are several instruments that we use for that. The Keck interferometer Nuller has been retired, and right now it's the LBTI in the mid-infrared. So this is a slide that you might remember from Steve's talk. Yes, I totally stole Steve's slides. So here you can see that indeed, so don't be fooled by the height of these columns. It's just it's the number of stars that were surveyed. Okay, it's not the number that were detected. So here with WISE, it's an all sky survey, so of course lots of stars were observed, but the level of detection is only 0.1%, and it's sensitive to very massive exozodies. With the Keck interferometer Nuller, it's getting better, and with LBTI we're actually reaching this threshold of 10 zodies that we were looking for. And so the NASA actually funded us to build the LBTI and execute a survey, because we want to know how we have to design these future exo-Earth imaging missions at best, in order to observe things and not just see dust. So the survey has been completed. We observed 38 stars. We had 10 detection, and it's all a work that was published by Steve earlier in 2020. And some of our main results, there's actually a clear difference between stars that have cold dusts that we know of. Okay, so stars with cold dust that we know of tend to have a much higher detection rate than stars that don't have detected cold dust. And I just stress that without detectable cold dust, because we shouldn't forget that analogs to the Kuiper belts in the solar system are currently not beyond within our reach. So this was somehow expected, because I said that we needed a population to replenish these exozodies. And also the most important result is that the median zodi level for Sun-like star is 3 zodies, which is excellent news for exo-Earth imaging. But we would like somehow better constraints for smaller missions, because so the simulations I showed you at the beginning, I think, were for a 9-meter telescope, and somehow with the decadal survey, they're just going forward to kind of smaller missions. So we need the threshold of 10 zodies might be smaller, so we need to refine that somehow. And how much time is left?
Actually, 0 minutes. Sorry, I didn't
okay,
you.
okay. Okay, I'm going quick. Okay, so we're going to renew the whole survey, upgrade our detector, change our camera, and we're expecting at least a factor 3 in improved sensitivity. We're funded by NASA through an XRP program, and we're going to go deeper and characterize individual systems. And also, I would like to highlight Denis Defrère is actually developing an instrument for the VLTI, which is going to give us access to the southern hemisphere, and in particular, it's going to work at 5 microns. So it's going to do the link between the mid-infrared we're seeing with LBTI and the near-infrared we're seeing with VLTI at 2 microns. So we can do the link between the hot and the warm dust. I leave my summary here, and I will take any question.
Thank you so much, Virginie. So if anyone has any question for Virginie about the whole survey. I don't see anything so far. I'm sorry for the frustration of cutting the questions for Laurent. And last talk, I saw a few questions popping up in the Slack after. Mm-hmm.
I'm going to take that as a compliment. It was all very clear.
Yeah, I'm sorry, I'm so not like inspired because like you kind of addressed all of the basic questions I had.
Oh, there's someone.
Roy, you can go ahead. Thank you, Roy.
Hi. So Peter, hi. Thanks for the nice talk. If you could go back to the slide where you have the pictures with the various amounts of Zodia and the Earth-like planet. I was not sure I completely understood it, because in the ones where you have a very high amount of Zodia, I also see bright sources.
Yes, absolutely. So this is actually the kind of structure that we're expecting to see, resonant trapping, clumps, the kind of structure that would be created by a planet. So above a certain level, you do not have access to the planet anymore, but you can see structures that they create. So that still gives us insight on what's in there. It's just that we have little hope to actually get direct light from this planet.
Okay, thanks. That clarifies.